Hi grade 9. So today we're doing lesson 6.4, which is reasoning about data. There's a handout on Teams that you should print and fill in as you watch this video. So at the top of your handout there is a box that says recall, and we're just going to define some terms there. So a conjecture is an educated guess based on the strength or existence of a relationship between two variables being considered. So you might say, I think there's a connection between time and how quickly this plant grows. So time and the height of the plant, I'm going to say, yeah, there's a connection. So to prove it, I would measure the plant every day and record it, and then see if that actually was true or not. So that's a conjecture. It's an educated guess. So a conjecture can be supported. That's the first blank there. Supported if there's an obvious relationship between the two variables. So in this case, the R squared value would be very high because the curve or line of best fit would closely match the data. The conjecture can be rejected if there's no obvious relationship between the two variables. So then the R squared value would be very low because the line doesn't match the data well. Note, the more data collected, the more reliable the conclusions made about the conjecture. So if you only looked at like 2 results, then you wouldn't really know if there was a relationship or not, because that's not very accurate. And then lastly, an outlier is a value that lies outside most of the other values in a set of data. So if I have a scatter plot and I have all these dots, and then there's one dot way over here, then this one would be the outlier. So it doesn't go with the rest of the data, but it's still part of it. So that's called an outlier, and you kind of just ignore that one. So example 1. Christina thinks that people with higher incomes donate more money to charities. She collects the following data. Do the data support Christina's conjecture? So we have their yearly income in thousands, and then we have the amount that they donated to charities. So we're going to graph this and just see if there's a connection between the two. So on the y-axis, you're going to have amount donated. And that's in dollars. And on the x-axis, you're going to have yearly income. And that's in thousands of dollars. On the y-axis, you can go up by 25. That'll give you enough room. So 25, 50, 75, 100. Okay. And then on the x-axis, go up by 5s. All right, so now I'm just going to plot these points. So 21, 310. 33, 450. So I don't really have room for that one on mine, but you will on yours. 40, 225. 41, 240. 46, 265. 55, 180. 68, 170. 87, 120. All right, so now I'm just going to draw a line of best fit. So that means it goes through 2 points and it goes in between them as well. So we want to have an even number on either side going through 2 points, and we ignore the outlier. So this one up here doesn't really match the rest of the data. So we kind of ignore that one. All right, so I'm going to go through 2 points and try to keep it in the middle of them. So that's right. I have 2 on each side, ignoring the outlier, and I go through at least 2. All right, so now we have to go back to the question, and this question says, do the data support Christina's conjecture? Well, she thinks people with higher incomes donate more money to charities. So higher incomes is at this end, and she thinks they donate more money to charities. But actually, that's not true from this data. This data shows that people with lower incomes donate more, and the trend goes down. So we're just going to write a few sentences about that. The data do not support her conjecture because it seems that the greater the income, the less money is donated to charities. We need more data before we can support this trend. After all, 1 out of 8 points was an outlier. So that's a pretty high ratio, right? So we would need a lot more data to see if this was actually true or not. But according to this data, her conjecture is not supported. All right, number 2. Allison hypothesizes that adult mammals' resting heart rates, measured in beats per minute, are lower for larger species. Do the following data support Allison's conjecture? So we have a list of animals there, and then we have their average resting heart rate, or their mean, and then their average mass in kilograms. So we have to determine which variable is independent and which one is dependent. So does the heart rate depend on the mass, or does the mass depend on the heart rate? Well, the heart rate depends on the mass. So that means that resting heart rate is going to be on the y-axis. That's in beats per minute. And then mass is going to be on the x-axis, and that's in kilograms. On the y-axis, you need to go up to at least 250. So it's very hard to draw straight lines on here. All right, so 25, 50, 75, 100, 150, 200, 250, 300, 350. And then on the x-axis, we need to go up to 518. So again, by 25. All right, and then I'm going to plot the data. So remember that we're doing the mass on the x-axis, so it kind of seems like the chart is backwards. So make sure you read the bottom number first. So 518, 58. 466, 52. 188, 70. 77, 75. 66.7, 116. 41.8, 79. 18.4, 83. 3.7, 257. And 0.5, 250. All right, so I'm going to use a curve to connect these. And it's just going to be quite steep and then flatten out. Now, looking back at the question, her conjecture was that the larger the animal, the lower the heart rate. So do the data support Allison's conjecture? Yeah, they do. So the larger the animal, the lower the heart rate. Let's write a few sentences about that. The data supports her conjecture. Since there's only a small quantity of data, it's hard to tell whether there's a strong pattern. More data would be helpful. In deciding whether the conjecture is helpful for a wider range of mammals. More data would be helpful in deciding whether the conjecture is accurate for a wider range of mammals. All right, so that completes the lesson. Have a look at the homework. That's what you'll be working on Tuesday, and enjoy your long weekend.